In this lecture, we take a look at the kinematics of a rolling object. That is, an object that is rolling without slipping. Okay, this is your first example of a situation involving an object that is undergoing a rotation and a translation. Rotation and a translation occurs simultaneously. The rotation is always going to be about an axis that passes through the center of mass when an object is undergoing a rotation and a translation at the same time. Axis of rotation passes through the center of mass. And all of this is with respect to an inertial reference frame. So consider, for example, this tennis ball. The tennis ball right now is rolling without slipping. The rotational axis passes through the center of mass. Okay, now because it is rolling without slipping, this would then be a different situation than an object undergoing a translation and a rotation. It's still rotating about the center of mass, but say instead it's doing something like this, like so. Okay, we're not interested in describing this kinematics for now. Instead, we're just going to describe the kinematics of a rolling object, rolling without slipping. Okay, now the axis of rotation, as I said, passes through the center of mass. If the axis does not pass through the center of mass, then the situation physically is much more complicated. So consider, for example, this slotted weight. This slotted weight is shaped like a cylinder, so then therefore the axis of rotation passes through the geometrical center of the cylinder. But because of the asymmetrical distribution of matter within this cylinder, the center of mass is not passing through the geometrical center of the cylinder. Therefore, the axis of rotation does not pass through the center of mass. When that happens, the situation is much more complicated. For example, say like so. Like that. Mathematically describing that motion is well beyond the scope of this course, so we're only going to consider what happens when the axis of rotation passes through the center of mass. Okay, now here's then how we begin to set this up in describing the kinematics of a rolling object. Okay, so first of all, let's say we have here a horizontal surface. That's the desk, for example. And then therefore consider the desk, consider the room here as an inertial reference frame. Okay, and then we have our rolling object. So here's my tennis ball, like so. Okay, let's say that right here is the center of mass, and the axis of rotation of the tennis ball passes through the center of mass. Okay, and then let's say it's rolling in this direction. So then therefore, with respect to the desk, and the desk, by the way, is our inertial reference frame, we'll just refer to this as O. With respect to the desk, right here, this point has a velocity in this direction, which we'll refer to as VCM. Okay, now the first thing that we want to understand is the velocity of the bottom of the ball here at this point of contact, and the velocity of the top of the ball relative to the desk, relative to the inertial reference frame. So how do we describe that? Well, what we do is we visualize this point right here, this point of contact, is what is called an instantaneous axis of rotation. Okay, now you're saying to yourself, what does that mean? Well, think of it like this. Because the ball is a rigid object, consider my elbow, for example, to be this point like so, the point of contact between the ball and the desk below. And then we have my lower arm here representing the ball as a rigid object. And because it's rolling without slipping, at any instant in time, we could picture the ball, for example, as rotating around my elbow, like so. Once again, this is referred to as an instantaneous axis of rotation. Now, because the ball is rigid, any point here like so along this diameter of the ball has the same angular velocity, omega, with respect to this point. In other words, all portions of my lower arm rotate through the same amount of angle per time. Let's refer to that as omega. And once again, that's with respect to this point right here, the instantaneous axis of rotation. Okay, now recall the following basic kinematics expression. V equals r omega. So let's say that right here is the radius of the ball. Call that r. And then therefore the v in v equals r omega is what I've already defined as VCM. But now let's take a look at the top of the ball. Relative to the ground, the top of the ball is moving in this direction with some velocity at this instant. We want to know what that velocity is. How far away, however, is the top of the ball from this point, the instantaneous axis of rotation? It's the diameter of the ball. It's the distance 2r. So then therefore, this speed right up here is going to be 2r, but then multiplied by the same value of omega. This then means that this speed has to be twice VCM. Think of it this way. The omega is the same at this point here and at this point here because the ball is a rigid object. Think of it as rotating around my elbow like so at this instant in time. So then therefore, all points along my lower arm turn through the same amount of angle per time. It's the same value of omega for all points. So then therefore, if the omega is the same, but I double the distance r, then I double the speed. Very simply, what this means is that the top of the ball's speed at any instant in time is twice that of VCM, nothing more than that. So this right here is 2 VCM, like so. Okay, well, what about this point right here, this point of contact here at this instant when we picture this in terms of the instantaneous axis of rotation? What is the speed of that point of contact relative to the desk? Okay, intuitively you say to yourself, oh, it's just equal to 0 at that instant, and you're right. And once again, it has to do with the expression v equals r omega. Because what is the r right here at this point when you're at the instantaneous axis of rotation? It's 0. So then therefore the velocity of this point right here at this instant is equal to 0 relative to the ground for that reason. Like so. Okay, this is the first step, if you will, in understanding the kinematics here of a rolling object, understanding that the top of the ball is moving at a speed at this instant that is double the speed of the center of mass, and the speed of this point right here relative to the desk is equal to 0 at this instant. Okay, now let's actually consider the rotation about the center of mass itself. In order to do so, we're going to switch reference frames. So now we're going to think of the center of mass of the ball as a moving reference frame, O prime. So now off to the side, O prime. O prime is the center of mass of the ball. And then consider the ball like so, where right here is its center of mass. What we now want to understand is the velocity of the top of the ball relative to the center of mass, and the velocity of the bottom of the ball relative to the center of mass. So right up here, I'm going to have a v prime. This right here is going to be the velocity of the top of the ball relative to the center of mass, the O prime reference frame. How do we calculate this v prime? We use Galilean relativity. So from Galilean relativity, of course, recall that v is equal to v prime plus u. So what's what here? Okay, well, first of all, the v. The v is the velocity of the object, the top of the ball, relative to the stationary reference frame. It's the 2 VCM. This right here is what we want. It's the velocity of the top of the ball relative to the center of mass, what we're calling v prime. And then we have the u. The u is the velocity of the moving reference frame, O prime, the center of mass relative to the desk, the stationary reference frame. It's VCM. Solve for V prime. V prime is equal to VCM. So VCM is the velocity of the center of mass of the ball relative to the desk. But it's also the same as the velocity of the top of the ball relative to the center of mass. This guy right here is VCM. This then means that VCM is equal to R omega once again, where the omega now is going to be about the center of mass. I'll illustrate further when I do one more step. Let's now take a look at the velocity of the bottom of the ball relative to the center of mass. Okay, this point here now we'll think of as the V prime. So using Galilean relativity, let's find the velocity of the bottom of the ball relative to the center of mass. Okay, so what's what? Okay, this right here is the velocity of the object, the bottom of the ball, relative to O, the desk, 0. And then right here is our unknown V prime. And then right here is U. This is describing the velocity of the center of mass. Velocity of the center of mass relative to O, the desk. That's VCM. Solve for V prime. Negative VCM. In other words, relative to the center of mass of the ball, the bottom of the ball is moving in the negative direction like so, with a speed that's equal to VCM. Like so. It's crucial that you understand these steps. It's crucial that you understand how to get the 2 VCM and the 0 here, first of all, relative to the inertial reference frame. And then we switch reference frames to consider the rotation with respect to the center of mass of the ball. And when we do, basically the speed of the top of the ball and the speed of the bottom of the ball relative to the center of mass is the same thing as the VCM. Once again, it's critical that you understand this in order to get the kinematics here of a rolling object. Okay, now because we know that, as I said a few minutes ago, we can now say that VCM is equal to R omega, where R, for example, is the radius of the ball, and the omega now is the angular velocity about the center of mass. That's the same thing as the angular velocity of this point right here, the instantaneous axis of rotation, as we picture the ball as rotating around my elbow. Okay, and then therefore, from this point, we basically just take a derivative for everything in order to describe the accelerations. So here's then how we describe the accelerations. Okay, now we're going to need tangential acceleration is equal to r times alpha throughout this description. Okay, just for the sake of argument, let's say that there's something pulling the ball, like my hand, like so, and the ball is speeding up in that direction, just so I don't have to worry about negative signs here in this basic description. So let's say at the center of mass, relative to the desk, is accelerating in this direction at ACM. Okay, now once again, picture this point here as an instantaneous axis of rotation. Consider the ball, origin object, to be my lower arm. And then at any instant in time, all points along my arm have the same angular acceleration about this point, the instantaneous axis of rotation. And then keep this expression in mind. So right here, we have the acceleration of the center of mass. Think of that as this, and it's equal to r times alpha. But then this point up here is once again a distance 2r away from the instantaneous axis of rotation, but the alpha is the same up here at this point as it is right here for this point. So then therefore the acceleration of the top of the ball is going to be 2r times alpha. That's twice the acceleration of the center of mass. Like so. And then once again, this point right here where r is equal to 0, the instantaneous axis of rotation, if r is equal to 0, at that instant the acceleration of this point is equal to 0. Like so. Okay, and then we switch reference frames. Now we go to the O prime reference frame. And then right here is the center of mass. Now what we seek to understand is the acceleration of the top of the ball, A prime, with respect to the center of mass. And then we'll do this for the bottom of the ball in just a moment. Once again, we do Galilean relativity. When we do the Galilean relativity, however, we don't use the velocity transform. Now differentiate it with respect to time to get the acceleration transform, which you guys haven't seen in class as of yet. Here's how you write the acceleration transform. Like so. This right here is the acceleration of the object with respect to O. This is the acceleration of the object with respect to O prime. This is the acceleration of O prime with respect to O. So what's what here in this description when talking about the top of the ball? This right here is the acceleration of the top of the ball with respect to O. That's 2 ACM. This right here is what we want, the acceleration of the top of the ball relative to the center of mass. And then this right here is the acceleration of the center of mass, the O prime reference frame, with respect to O, the desk. That's ACM. Solve for A prime. What do you do? No surprise, it's ACM. So then therefore, the acceleration of the center of mass of the ball relative to the desk is the same thing as the acceleration of the top of the ball relative to the center of mass. Like so. And then we do the same thing for the bottom of the ball. So at the bottom of the ball, we've got an unknown A prime like so. Once again, we use Galilean relativity. Okay, so what's what in the Galilean relativity? This right here is the acceleration of the bottom of the ball, the object with respect to O, the desk, 0. This is what we want, the acceleration of the bottom of the ball relative to the center of mass. And then this right here is the acceleration of the center of mass relative to the desk. That's ACM. Solve for A prime. Negative ACM, like so, no surprise. So relative to the center of mass, the bottom of the ball is accelerating in that direction with a value of ACM. This then means that we can write the acceleration of the center of mass using the R alpha equation, the same thing as the tangential acceleration equation when looked at from the O reference frame. Once again, take yourself through these series of steps, understanding first of all the velocities and then the accelerations at the top of the ball and the bottom of the ball relative to the desk, and then how we switch reference frames to describe all those quantities with respect to the center of mass. Once you've taken yourself through that, however, in terms of the basic kinematics of a rolling object, any problems that you'll encounter are actually pretty simple and straightforward. So let's go ahead and take a look now at an example involving a rolling object. It's going to be involving this ball, which will eventually slow down and come to rest. So let me do some erasing here first. Okay, and then here's our problem. Copy it down as I read it. Okay, a ball with a radius of 3 centimeters, that's roughly like so. For example, we'll say with the tennis ball, it rolls without slipping on a horizontal surface. The ball is initially moving at 2 meters per second and it comes to rest after rolling 7 meters. Okay, so let's begin to diagram this out. Like so. Okay, so here's the ball. Okay, right here is its initial velocity in this direction. We'll just call it V0. This is equal to 2 meters per second. And then eventually ends up at rest. And the final velocity V is equal to 0. And it comes to rest after rolling a total distance of 7 meters. So let's say from center of the ball to center of the ball, like so. This right here is our total distance x of 7 meters. Okay, the radius of the ball, call it small r, is given as 0.03 meters. That's 3 centimeters. And now in part A of the problem, it asks for us to calculate, first of all, the linear acceleration. Okay, now in order to calculate the linear acceleration, we'll just go back to one-dimensional kinematics from chapter 2 and specifically use the third kinematics equation. Okay, v squared is equal to v0 squared plus 2a times x minus x0. So recall the good old days here of chapter 2, nothing more than that. So final velocity of 0, set the x0 equal to 0, and then just solve for a. So, and now just punch in your numbers. Easy enough. Remember, of course, what the negative sign means for the acceleration vector. We'll see then how this relates to the rotational quantities directions as well in just a few moments. But for now, let's just get the number. All right, so V0 squared, so that's 4, and then divided by 2 times 7, so divided by 14. This is about negative 0.29 or so, give or take, meters per second squared. Okay, let me move my file. Okay, and now let's specifically relate the directions of all of the vectors to each other. So the translational acceleration vector is negative. It points to the left-hand side like so on the diagram. Therefore, we have to, using right-hand rule, define the positive direction and the negative direction for the rotational vector quantities in the following way. Watch this. The ball is rolling like so. I'm calling V0 to the right-hand side a positive number. Therefore, the initial angular velocity omega naught, V equals R omega, is equal to V naught over R. And it has to also be thought of as a positive number. In which direction is that pseudo vector? Watch this. Ball is rolling like that. Therefore, the initial angular velocity vector omega naught points into the board. We're calling that the positive direction. When you draw a vector, by the way, that is into the board, you'll see the following symbol to describe it. Like so, a circle with an X through it. It represents the back end of an arrow. That means into the board. So then therefore the omega naught vector is positive into the board by definition. Okay, now let's continue the math. It says in part B of the problem to find the angular acceleration. There's a couple of different ways in which we can solve this problem. However, in part B, probably the easiest way to solve it is to use the tangential acceleration expression. That is, tangential acceleration is equal to r times alpha. Okay, now specifically this refers to the acceleration of a point, for example, say on the top or the bottom of the ball with respect to the axis of rotation, with respect to the axis of rotation. That is, however, the same thing as the acceleration of the center of mass, as I went through a few minutes ago in the kinematics, the acceleration of the center of mass with respect to the desk. So then therefore think of this as our ACM, which is just A. And now let's solve for alpha. So alpha is then therefore going to be A over R. Notice it's going to be a negative number. So I take the A, negative 0.29 meters per second squared, which is still in my calculator, and divide by 0.03 meters. And this comes out to be negative 9.52 about radians per second squared. Notice the negative sign. Therefore, in which direction is the alpha vector? It's out of the board. Here's how the pseudo vectors work as the ball slows down while rolling in this direction. So consider first of all initially, as I described earlier, omega naught is into the board like so. And then the ball eventually slows down and comes to rest. So then therefore using the tail to tip method of vector addition, in which direction is the delta omega vector? Watch this. Omega naught plus delta omega is equal to omega. The final value of omega is equal to 0. Therefore, we have omega naught plus delta omega equals the final value of omega, which is 0. The delta omega vector points out of the board. Therefore, the alpha vector points out of the board. Hence, the negative sign associated with that quantity. Now, how do you describe a vector pointing out of the board on a diagram such as this? You'll see the following symbol. A circle with a dot in it like so. This is representing an arrow that is pointing straight at us like so out of the board. So the alpha vector, the angular acceleration vector, points out of the board for that reason, hence the negative sign. Once again, take yourself through the positive signs and the negative signs of this example and make sure you understand how the directions work. Okay, and then lastly, we have part B of the problem solved. Lastly, it says how many rotations were made. There's a couple of different ways, once again, to solve part C of the problem. The easiest way to do it, however, is just take the distance here of 7 meters that we were given and then do the following. think of the distance x as some multiple, we'll call it n, of circumferences, where the circumference is 2 pi r. So then therefore, the number of rotations made is going to be the value of x divided by how much one rotation is, which is the circumference. So then therefore, just take 7 meters and divide by the circumference of the ball. 2 times pi times 0.03, and this works out to be about 37.1 rotations or revolutions. Okay, as I said, there's a couple of different ways in which we could have done this problem. We could, for example, find the final angular position theta, and then from there convert it from radians into the number of rotations made. Ultimately, you would end up with the same answer as this, okay? Okay, that concludes the kinematics of a rolling object.